Now we will take a look at some applications or advanced rules that we will not go into greater detail, but will be still useful for understanding the basic terms that we have been discussing now. The first thing is why linear approximations. So, that is the first question that comes to mind. Linear approximations are fine, but what is so special about them? Right? We have been approximating f of x by the linear approximation of f around some point x star. This is what you have been doing, but you could argue that there is nothing special about linear functions and you can go higher, and in fact you could do that, and that is the fundamental idea behind higher order approximations. The linear approximation would simply say that f of x is approximately equal to f of x star plus f dash of x star into x minus x star. This would be the linear approximation. But you could go higher order approximations and have a quadratic approximation instead, which would say f of x is approximately equal to f of x star plus f dash of x star into x minus x star plus, here is the half f double dash of x star into x minus x star the whole square. This is called a quadratic approximation. So, both of these are valid around x approximately equal to x star. The second expression, the first expression is the linear approximation. The second expression is the quadratic approximation. Both of these are approximations, but the second is a better approximation than the first. But it comes at a cost. It is significantly more complex. It is a quadratic term here as opposed to just a linear term here. And for example, for a special class of functions, quadratic approximations are exactly equal to the function itself. And the classic case for that is f of x is equal to, let us say, x squared itself. One, let us say f of x is equal to x squared, in which case f dash of x is equal to 2x and f double dash of x is simply the derivative of the derivative, which is equal to 2. Let us pick any x star, it does not matter. X squared is approximately equal to x star squared plus f dash of x star is 2x star into x minus x star. So, which is, and then you have a quadratic term which is 1 by 2 into 2 into x minus x star the whole square, which is exactly equal to x squared. So, you end up with the approximation being exactly equal to the function, because the function itself is quadratic in nature. A quadratic approximation is going to give back the original function itself. That is not true for all functions. For example, you could have e power x instead. If you approximated e power x around x equal to x star equal to 0, e power x around x star which is equal to 0, right, approximate e power x. So, e power x would be approximately equal to e power 0 plus e power 0 into x minus x star plus e power 0 into half into x minus x star the whole square. So, x star is 0, which is 1 plus x plus x squared by 2. So, if you are all familiar with the Taylor series, this is exactly what it is. So, the linear approximation truncates it at the linear term. The quadratic approximation truncates the Taylor series at the quadratic term. You could in principle go up to cubic, quartic, quintic and so on. In most machine learning applications, you will stop at the linear approximation. There are certain situations where you will go to the quadratic approximation, but in no practical scenario will you ever go beyond quadratic approximations. Here is a couple of examples where quadratic approximation will actually be useful. Here is an exercise question. Which is closest to 1.1 power 7? 1.1 power 7. The 4 options are 1.7, 1.9, 2.1 and 2.3. If you did a linear approximation, you know 1.1 power 7 is simply 1 plus 7 into 0.1, which is 1.7. That is what, and that makes the compound interest, simple interest logic clear. That is 1.1 power 7 means that every year your money grows by 10%. So after 7 years, if you use simple interest, you would just get 1.7. But that is not what we are asking. We are asking for compound interest. So with 7 years 10%, simple interest is no longer a good approximation of compound interest, and in fact you would expect more. And you can get that using a quadratic approximation. Linear approximation would give you 1.7, and the truth is you can compute the truth using your calculator. What does a quadratic approximation give you? We will compute that now, which is f of x is equal to 1 plus x power 7. F dash of x is 7 into 1 plus x power 6. F double dash of x is 42 into 1 plus x power 5. We want to approximate f of x around x is equal to 0 and evaluate it at 0.1, right. So, f of 0.1 is approximately equal to 1 plus f dash of 0. What is f dash of 0? Okay, I think we can do one more step here. F dash of x is this, f dash of 0 is equal to 7, f double dash of 0 is equal to 42. So, 1 plus f dash of 0 into x minus x star would be 1 plus 7 into 0.1 plus half into 42 into 0.1 the whole square, which is 0.01. So, this is the reason why you can ignore the quadratic term in a lot of cases, because 0.01 is negligible when compared to 0.1, but this term can overwhelm, right. So, that is the reason why you can in principle, instead of 0.1, if you had 0.01, so this term would be 0.01, this term would be 0.0001, in which case you can in principle ignore the second term. But in this particular calculation, you will see that you can't do that, and you will actually get 1.91 would be your second order approximation, which is much more closer to the truth than the simple first order approximation, which would have given you 1.7. So, here is an example situation where the second order approximation gives you much better, much closer results to the truth than the first order approximation. Okay. Yeah. With that, we will move to the next advanced application. So, yeah, the higher order approximation or quadratic approximation is simply a detour to show that higher order approximations can exist and might be useful, but for most situations we will not be bothering with higher order approximations, and we will just stick to the linear approximation, which is what we are going to be doing to the rest of the course also. Right. So, now we will come to the product rule, which you are all familiar with, but we will do that from the point of view of linear approximations. Let us say f of x is equal to g of x into h of x. Note that right now we are working with all one dimensional functions, which is functions from reals to reals. Let us say you have a function f of x, which is g of x into h of x. Now you want to know the derivative of f with respect to x. How would you know the product rule already, but let us try to get to the product rule using the idea of linear approximations. So, f dash of x is what we want, right, f dash of x. Now we will do linear approximation of f, right. F of x is approximately, we will do linear approximation of g and h separately. Right? F of x is approximately g of, let's pick x star is equal to 0 for now. You can pick any x star, but life will be easier if you just pick x star is equal to 0. G of 0 plus x times g dash of 0. That is, this is simply the linear approximation of g of x around x star is equal to 0. H of x would be h of 0 plus x into h dash of 0. This is equal to g of 0 into h of 0 plus x into g dash of 0 h of 0 plus h dash of 0 g of 0 plus x squared. You have x squared term and that will be g dash of 0 h dash of 0. You did a linear approximation of both the terms, but you ended up with a product. You have something else, you have a quadratic term also. So, if you want a linear approximation, you can just ignore the quadratic term here, and that means that your Lx of f is simply equal to g of 0 into h of 0 is simply exactly equal to f of 0. F of 0 plus x into f dash of 0, which means that f dash of 0 is simply exactly equal to g dash of 0 into h of 0 plus h dash of 0 into g of 0. So, this is the product rule which we derived from first principles based on the idea of linear approximations coming from derivatives. We did a linear approximation of each of these individual components and we did a simple product and we ignored the higher order terms. And this corresponds to a linear approximation. By just matching terms, we get g of 0 and h of 0, which is exactly equal to f of 0, and this term, so that this term must correspond to f dash of 0. You get the product rule back. Similarly, you can do the same thing for the chain rule also. Let us say f of x is equal to g of h of x. Right? Let us say you want f dash of 0. We will first approximate f of x by the linear approximation of g around h of 0, right, which means that g of h of x is approximately h of 0 plus h dash of 0 to x. We are approximating h first by right, we will first approximate h around 0, right. H of x is approximately equal to h of 0 plus h dash of 0 into x. So, now we have g of h of 0 plus h dash of 0 into x, which we will approximate this using a linear approximation of g around h of 0, which would be g of h of 0 plus g dash of h of 0 into h of 0 plus h dash of 0 x minus h of 0. So, this essentially becomes g of h of 0 plus g dash of h of 0 into h dash of 0 x. But we know that the linear approximation of f is f of 0 plus f dash of 0 into x. So, this is exactly equal to f of 0, and that means that this term must be equal to f dash of 0. By matching terms, we get okay. So, I will have to put a lot of squiggly equal to's here. These are not exact equal to's, all of these are approximately equal to. This first approximation is because of approximating h of x around 0. The second approximation is because of approximating g around h of 0. We substitute match terms together, we get we know f of x, linear approximation of f of x is f of 0 plus f dash of 0 x, which means f dash of 0 is exactly equal to g dash of h of 0 into h dash of 0. So, once again, this is not a surprise for anyone here. We have just derived the chain rule, which is one of the most basic rules here. but you can get back the chain rule also from the idea of linear approximations. Okay. So, we will do some simple examples for getting the derivatives. You could in principle just do chain rule every time, but we will try to get it from the linear approximation idea. Right? So, just e power, let us say you have f of x is e power 3x by square root of 1 plus x. Let us say this call is f of x, and we want the linear approximation of this around x equal to 0. That means that we will pick x star to be equal to 0 and we will approximate this function around x star equal to 0. You could just view this as a single function and you could get the derivative using chain rule and write f of x is equal to f of 0 plus x into f dash of 0. You could do that, or you could just do linear approximation from first principles and do each of these terms separately. Just e power 3x by square root of 1 plus x is approximately equal to 1 plus 3x, because the linear approximation of e power 3x is simply 1 plus 3x, and the linear approximation of 1 plus x power minus 1 by 2 is 1 minus x by 2. So, if you do a product, you will have the a constant term, a linear term and the quadratic term. The quadratic term you can ignore, which if you do, you get 1 plus 5 by 2x. You would have gotten the exact same answer if you had found the derivative of this function at x equal to 0, which would be 5 by 2. But it is also nicer to see that this a more natural way of doing this is to just do linear approximations of each of these components and work on it later. So, this is a direct application of the product rule and the chain rule also. So, what is, let us say you want the linear approximation of so the question is, give linear approximation. So, give the linear approximation of let us say e power square root of 1 plus x around x is equal to 1. So, just to give a variety here, we have always been doing x equal to 0, you could also do x around x equal to 1, right. So, you could once again just compute f of 1 and f dash of 1 and be done with it. You could do that just as well, and you could also just find the linear approximation of each of these terms around x equal to 1 and be done with it, right. Either way, what you would get is e power square root of 1 plus x. This is an exercise for you. E power square root of 1 plus x is approximately equal to e power square root of 2 plus e power square root of 2 by 2 root 2 into x minus 1. Right. Once again, whenever you are using squiggly equal to, always approximately equal to, give the conditions, which is the first thing, it is around x equal to 0, this is around x equal to 1. So, linear approximations are really I think I have been emphasizing it again and again and again. Linear approximations are the key tool that allow you to get around most of machine learning with its very complex functions. You can't really handle general functions, that is the reason why you do approximations. Okay. So, finally we move to the last application, which is regarding maxima, minima and saddle points. This is something which you would have seen in your mathematics too as well, but this is what I am going to say. It is, you have your linear approximation of f around x star as f of x star plus f dash of x star into x minus x star. There is a very special case where you have f dash of x star is equal to 0, then your Lx of f is actually not a function of f at all, but rather it is a constant. If f dash of x star was 0, that means that Lx star of f is equal to f of x star. So, even though this is a function of the left hand side is a function of, supposed to be a function of x, it is a constant. And such points where f dash of x star is 0 are called critical points, and these points are generally interesting in one way or the other. And for example, in the case of one dimensional functions f from r to r, f dash of x star equal to 0 means that that point x star is either a maxima or a minima or what is called a saddle point, right. But let us write down that first. F dash of x star equal to 0 is saying that it is a definition for the statement, that is x star is a critical point of f. If you have a point where f dash of x star is not 0, it is clearly that function is varying around the neighborhood of x star, right. So, I have let us say if f dash of let us say Lx star of f at some point the linear is equal to let us say 7 plus 3x, does not matter much, but I am giving an example where because Lx star of f depends on x, what this says is at the neighborhood of x star there is a dependence on x, which means that there is a variation. But if you did not have a dependence on x at all, something like Lx star of f is equal to 7, what this says is around x star there is no variation, it is actually a constant. And when can such a thing happen? Such a thing can happen only when x star is either a maxima or a minima or a saddle point. What are these? What do these terms mean? Here is an illustration of that. Right. So here is an example function, and if you considered this point as x star, this was x star, your linear approximation would be exactly equal to a constant, because this the derivative of the blue function here at x star would be 0. So, the linear approximation would be a straight line. And in this case x star happens to be a local minima, or we will just call it minima. But that is not the only kind of place where there is no variation. There is also the second function here where your x star is this, and your linear approximation of this function around x star is also a straight line. And this particular point happens to be a maxima. These are the two really main cases, but there is also one tricky case which is I have not drawn perfectly because it does not seem like a maxima or minima, but such a thing like this is also possible, where your function reaches a slope of f dash of x is equal to 0 and then it increases again. This particular point is neither a maxima nor a minima. I mean, if it is essentially a maxima of this part and a minima of this part. So, such a point is called a saddle point. This is an example of critical point being a minima. This is an example of a critical point being a maxima. Second, and finally this is an example of a critical point being a saddle point. Why is it called a saddle point? In higher dimensions you will see that this does really look like a saddle, at least in 2 dimensions it does really look like a saddle. Even in 1 dimension you can imagine this kind of looks like the back of a horse. So, this is called a saddle point. So, critical points are particularly interesting for several functions, mainly because machine learning is really at its core is just an applied optimization problem, and you are interested in finding the minima or maxima of functions, and so we are really interested in finding points in the function where the gradient or the derivative is 0. The derivative is 0, that means that that particular point is a critical point and hence an interesting point. It can potentially be a minima or a maxima. With that we wrap up the univariate calculus part of the syllabus, and we will move on to multivariate calculus